Welcome to John Lewis Memory School. The topic is the reaction mechanism of esterification. Imagine you want to capture the sweet scent of a fresh pineapple or a ripe banana in a laboratory. To do that, we need to join a carboxylic acid and an alcohol together to form an ester. But these two molecules don't just snap together like magnets. They are actually quite content on their own. To get them to react, we need to orchestrate a sophisticated molecular dance, driven by an acid catalyst. Let's look at our starting materials. On one side, we have a carboxylic acid with its distinct carbon-oxygen double bond. On the other, an alcohol. Our goal is to replace the OH group of the acid with the OR group from the alcohol. The first step is all about making the acid more attractive. Notice the oxygen atom sitting at the top of the carbonyl group. It has two lone pairs of electrons just waiting for something positive. When we add our acid catalyst, a stray proton, a hydrogen ion, approaches. Watch as a lone pair from the carbonyl oxygen reaches out to grab that proton. This is protonation. By taking on that extra positive charge, the oxygen makes the carbon atom directly below it much more electrophilic. In other words, that carbon is now hungry for electrons. Now look at the alcohol molecule. Its oxygen atom is also rich with electrons. Seeing that hungry carbon center, the alcohol's oxygen attacks. As you can see here, a lone pair of electrons from the alcohol forms a new bond with the carbonyl carbon. But the carbon can't have 5 bonds, so the existing double bond breaks, pushing those electrons up onto the top oxygen. This brings us to a crucial moment, the tetrahedral intermediate. Everything is crowded around that single carbon atom. To move forward, we need to rearrange the furniture. This is the proton transfer. Notice how the proton that came with the alcohol is now feeling the squeeze. It shifts over to one of the OH groups. Why does this matter? Because by adding that proton, we've turned a poor leaving group, a hydroxyl, into a magnificent leaving group, a water molecule. Let's visualize this. The water molecule is now essentially packaged and ready to depart. Here is the key insight. To push the water out, a lone pair of electrons on the other oxygen swings back down to reform the carbon-oxygen double bond. As that bond forms, the water molecule is kicked out. This is the elimination step. We're almost there, but our brand new ester is still carrying that extra proton from the very beginning. In the final act, another molecule, perhaps the water we just released, comes by and picks up that extra proton. This is deprotonation. Look at what we've achieved. The acid catalyst we started with is regenerated, and in its place we have a sweet-smelling ester. We've broken old bonds and forged new ones through a precise exchange of charge. The next time you smell the fragrance of a flower or the zest of an orange, remember this microscopic choreography. It's a beautiful reminder that even the most complex scents in nature are just the result of electrons seeking balance, one shift at a time.